Hey folks, my name is Siddharth Karamcheti and I'm a fourth year PhD student at Stanford. I'm thrilled to present a system, LILAC, that we built for language guided robot manipulation with online language corrections. I jointly led this work with Yuchen with amazing collaborators Raj and Nidhya. I want to start with some motivation. What are the common failure modes of current strategies for learning for control? Let's say I want to execute on throw the bag of chips away. How would a fully autonomous end-to-end imitation learning approach fare? Well, we see that it overshoots to the left of the bag of chips, then goes out of distribution. It ends up just continuing to overshoot, driving it to the shelf, damaging the environment. Given limited data in these end-to-end settings, these sorts of catastrophic failures are common. So what about alternative learn methods? Let's say shared autonomy for assistive control. Well, things are a bit better now that a human is controlling, but we get stuck in this region just a bit to the left of the chips. We can't make progress, so we just give up. Looking at these two examples, it's really sad that we have these approaches that are able to get 80% of the job done, capture the right message, but then just fail. If only we could intervene somehow, just nudge the robot just a little bit to bring it back on course. Maybe physically intervening isn't feasible in all settings, but what if we could just say no to the right and have the robot adapt to us in real time? This is by no means a new idea. Past work does this in a variety of ways, but they tend to be limited. For example, a lot of prior approaches assume that we can provide corrections after the robot executes. Roll out, fail, correct, then try again. This is okay in some settings, but just like we're seeing on the left, sometimes we just can't recover from the mistakes the robot makes. Which brings us to today. We're going to talk about building a system within the shared autonomy paradigm pictured on the right that can adapt to real-time streaming language corrections, learning from only a handful of demonstrations spanning multiple tasks. We call our system LILAC, Language-Informed Latent Actions with Corrections. It's very much rooted in prior work on latent action controllers for assistive teleoperation. To give a short primer, I want to consider a robot, environment, and some task description. Rather than learn to execute actions autonomously in the environment, the robot is going to take a data set of demonstrations, then learn and expose a low-dimensional control space for the human to use. The human is then going to use this control space to work collaboratively with the robot. Instead of controlling individual end effector directions, forward, backwards, left, right, up, down, these spaces are more semantic and state dependent. Pushing up on a joystick might bring you closer to the bag of chips, while left, right may allow you to better align the gripper to make it grasp. Let's make this more concrete. Here's a demonstration of a single motion for sweeping across a table. Learning a latent action model from this demonstration can produce a control space where pushing right moves the robot across the table, while pushing down initiates the sweeping pattern. Let's dive a little bit more into taking a look at how we learn these models by looking at the LILAC objective and architecture. LILAC takes in the robot's state, the state of the environment, and language. In general, we're going to treat learning a control space as a state and language condition compression problem. Learn a low-dimensional manifold that we can use to reconstruct the actions seen in our demonstration data. We'll encode state with the learn MLP, and we'll encode language with a pre-trained language model. Now, the secret to LILAC, different from prior work, is in this language gating module. We'll talk about this more in a bit, but at a high level, it controls how much attention we pay to features of the environment versus the language. For this language instruction, we pay attention to all of the features of the state, setting the weighting parameter alpha to 1. But for another utterance, like tilt down a little bit, we don't really care about the positions of the objects, so we're going to set alpha to 0. When we combine the two representations subject to alpha, we then learn a separate MLP to produce a control manifold, which we represent as a set of basis vectors spanning the robot's action space. At train time, we then learn an MLP that compresses the ground truth high-dimensional robot action to weights on these learned bases, which we then combine to reconstruct the original action, again akin to an auto-encoding or compression problem. At inference time, a human is now actively controlling the robot, so we discard the learned action encoder and directly use the output of the human's interface, a joystick, for example, to weight the state condition bases producing robot actions to execute. Looking at these details, the important punchlines are that we are 1, producing control spaces for the human based on the current state of the environment and task description, and that 2, we're somehow using this gating module to fuse state and language in different, nuanced ways. This last part is actually the key insight of this work. We show that this language-driven gating is key to allowing us to learn these models with only a handful of demonstrations and scale corrections to a variety of different contexts. Let's try to understand this just a little bit better. Let's consider the language, let's throw away the chips, and ask what we need to look at or pay attention to in the environment to facilitate generalization. Minimally, we need to localize the bag of chips and trash can, and maybe some other obstacles in the scene to avoid collisions. In general, though, this language utterance is highly tied to the state of the environment. But if we consider tilt down a little bit, there aren't really objects in the state to point to that we actually need to pay attention to. It doesn't really need state information, and if that's true, maybe we can exploit that. The goal of the gating module is to filter out environment information when interpreting these more corrected language utterances, enabling huge gains in sample efficiency. We don't need to collect demonstrations of tilting down a little bit in dozens of different contexts. Because it's state independent, we can learn to ground this correction with only a single demonstration. How do we acquire this parameter alpha? Well, we make the realization that state dependence is a feature of language and maybe a little bit of common sense understanding. And we have tools, specifically large-scale language models, that are pretty good about reasoning about both. So we construct a simple prompt asking for a rating for the amount of extra information needed for a given utterance, pass it to GPT-3, and then use the output to set our alpha values. Here's what LILAC looks like and sounds like in practice.
Let's throw in chips. Stuck a little. Can we move backwards just a bit? All right, now left a tad. Thank you very much. Backward some more. Thank you. Perfect.
This conversational interface is natural and seamless and allows users to quickly recover from any failure modes during execution. This is demonstrated by the success rate over approach compared to imitation and single-stage latent action baselines, where we see that LILAC dominates in subtask and full task completion. In general, in a real-world user study, we find that LILAC is both performant and preferred by users. So where do we go from here? We built our system in the shared autonomy paradigm because of its practicality and ability to scale. But looking at more collaborative split autonomy settings, closer to imitation learning or fully autonomous control, feels like a natural next step. We'll definitely need to collect more data, but hopefully our insights around gating hold true. Other than that, looking at different types of corrections, and more importantly, learning from user corrections online, seem like promising areas of research. Thank you all so much. Looking forward to seeing you throughout the conference. Thanks.